Optimizing index strategies. So as you can see, 70-464 is loaded with indexing objectives that span many different areas of the exam. So far, we've learned how to create them, we've learned how to maintain them, we've learned how to design them by tuning and optimizing queries. So we've really done it all. So this is just going to be a brief nugget to go over a lot of those important areas and take a high-level look at what kind of strategy we should employ for each major kind of index. So we'll talk about what strategies are usually employed for clustered, non-clustered, and column store indexes. We'll also get some guidelines in there and talk about what the optimal number of indexes is for an OLTP versus a data warehouse type database. Then we'll jump into the virtual nugget lab. We'll look at clustered indexes, specifically just identity versus globally unique identifier, and when you should use one over the other. We'll also get a demo going for non-clustered indexes. We'll just get a base non-clustered index going. We'll add included columns into it, filtered columns into it, and really what we'll do there is we'll take a table we haven't indexed and we'll put a couple of indexes on it to see how it works. And at the end here, we will head over to the AdventureWorks 2012 DW database, which is the data warehouse, the sample data warehouse for AdventureWorks 2012. And we'll use a column store index. I'll show you how we can put a column store index on one of the bigger fact tables over in that database and see what kind of performance gains we can get from it. So again, a lot of this stuff we've already covered. We're just going to look at it again from a higher level and then get some different demos going so we can get a new perspective on how all this stuff works. So when it comes to index strategies, the first thing we need to talk about is clustered indexes. Remember, a clustered index is one that physically stores the data sorted on disk by the key. Now, before I even go any further, anybody know what a heap is? A heap is a table that contains no clustered index. It's just a pile of data, not logically or physically sorted in any order. So that brings up the question, then are heaps bad? Is there any situation where I would want to use a heap? Or in other words, is there any situation where I wouldn't want to use an index? And the answer to that is rarely. Rarely. As a best practice, we should have a clustered index on every table, but there are cases, very, very, very tiny table cases, where it won't be beneficial to put a clustered index on it because SQL Server will probably choose to do a table scan anyway. So the cost of having and managing and maintaining a clustered index on a small, really small table would be greater than not having one. So heaps are bad most of the time because it's just a big pile of unorganized data, and it's a lot more I/O and work for SQL Server to do. Clustered indexes bring organization to that big pile of random data. It's going to physically sort and store the data in order on disk by the key. The key being the field we choose when we create the clustered index. It's also going to form the base for all other non-clustered indexes, which are just going to store pointers to where that data sits inside of the clustered index. And this is why it's really important to choose a clustered index key that is static, one that doesn't change. Because if we choose a field that's modified, then anytime that clustered index key is modified, SQL Server has a lot of reorganizing to do at the physical level, and then all the non-clustered indexes need to be changed underneath the hood as well to point to those new locations. Equally important here is having a narrow key for our clustered index. The reason this one's important is because non-clustered indexes are going to store the clustered index's key in their index as their pointer. So if we have a wide key, now all of our non-clustered indexes are going to store that wide key, and it's going to require a lot more data pages, which is going to equate to more I/O, more memory, more CPU cycles, more work for SQL to do. So static, narrow, very important. Unique is also important because if we choose a clustered index key that isn't unique, SQL Server is going to make it unique by appending 4 bytes to the end of it, which is really just going to play in here to how narrow our key is. Because if we do not have a very unique column, then all of a sudden here we're not going to have a very narrow column either. And finally, we want a sequential key, one that is ever increasing. This will guarantee that when that new data comes in, it's going to be placed in order at the end of the index. If it's not sequential, SQL Server is going to have a lot of shifting to do, which is going to create fragmentation and is going to create some problems. So sequential key is going to be ideal. So these are the 4 characteristics of an amazing clustered index key. Just whenever you choose your clustered index key, just ask yourself these 4 questions. Is it static? Is it narrow? Is it unique? And is it sequential? Then you have chosen the key for your clustered index wisely. Just a few other things to note about clustered indexes. As we mentioned, almost every table should have one, except in those rare cases where a heap is okay. Identity columns. These are good because they follow all of the best characteristics of a clustered index: static, narrow, unique, sequential. The downside, though, is it doesn't really describe the data in any way. So if you can find a natural key, that's great. But if you can't, don't force it, because a lot of times if you try to force a natural key, it will not be one of these characteristics. So identity columns are okay. GUID columns, as we've seen in previous nuggets, are okay. But the big problem is that they are not narrow. They're wide. So while they may solve the problem of generating unique IDs anywhere, they create another problem in that they're not the greatest clustered index key. Also, they're not sequential by default. We can use the new sequential ID, but even that has a hitch to it, and that is if you reboot the server, there's a chance that it'll start generating them sequentially from a point prior to the most recent one before the server is rebooted. So the general rule of thumb here is only use GUIDs if you absolutely have to. Multiple columns are generally going to be bad because, again, we're going to bump up against this narrow characteristic. So composite keys, try to stay away from them. There is a scenario where it's okay, though, and that is where you use intermediate tables. Usually when you create an intermediate table, it's going to have a couple of keys in there so you can represent a many-to-many relationship. And a lot of those times, those are going to be integers. So a couple of integers as a composite key is going to be okay because it's still going to be pretty narrow. But again, if you're using a composite key that's comprised of natural keys, then you could get in trouble. So the greatest strategy when it comes to clustered indexes is to just pay attention to these four characteristics. Non-clustered indexes are going to be the workhorses of performance when it comes to our databases. So these are going to be the important ones. And these are separate index structures that are logically sorted, and they just point to the physical data. Whether that physical data is a heap or it's on a clustered index, it's going to point to one of them. If it's a clustered index, it's going to use the key as its pointer. If it's a heap, it's going to use the row ID as its pointer. So that's what non-clustered indexes are all about. They're most commonly used for search columns. Anytime we define an index, we should analyze our queries, look for the predicates, look for all those filters in the where clauses, and try to create indexes that include anything that's inside of the where clause. And that will increase our chances that it can pull all the data from the indexes rather than have to go into the data pages, which will give us huge performance gains. Filtered indexes are another really good one. As we saw in a previous nugget, this is a way that we can create an index on a subset of data. Great for sparse columns, or great for popular subsets of data, because we can really speed up queries that hit that subset of data. And another one that we've mentioned quite a bit, one of the greatest strategies when it comes to non-clustered indexes is indexing your foreign keys. That is a best practice, and you should pretty much always do it. We also took a look at column store indexes, which is just a great way to speed up access to very, very large amounts of data, large tables. So that's why it's really meant for the OLAP data warehouse world. And just remember, if you create these, to include all the columns, because you can only have one column store index per table. So you create an index that spans all of the columns. That table will then be read-only, and we'll get a massive, massive performance boost. Finally, some strategical guidelines here. The first one's a good one. I get asked this question all the time. I see it get asked all the time. How many indexes should I have per table? And a good general rule is keep it under 10 for OLTP environments. Now, this will change depending on the type of table you're indexing. If you're indexing a table that is very rarely hit with inserts and updates and deletes, then you could probably go a little above 10. On the flip side, if you have a table that's extremely busy, then you probably want to go far less than 10. But generally, a good rule of thumb is 10 indexes or less for OLTP environments. In the world of data warehousing, it's the opposite. We're the ones responsible for loading up data warehousing with our ETL loads. So what that means is there should be no activity or very little activity against our data warehouse. So we're only concerned about read performance. We could care less about inserts, updates, and deletes. Therefore, we should index to our heart's content. Also, don't forget about fill factors, data typings, and defaults. These are three things that we can use, three strategies that we can employ to decrease fragmentation. So with the fill factor, if we have a table that does have high activity and we're seeing a lot of fragmentation, that means a lot of page splitting is going on. And so we can decrease the fill factor so it leaves empty space on the pages, which will ultimately lead to decreased fragmentation. And don't forget about choosing the right data types and also specifying defaults when you can, because these will also cut down on fragmentation. All right, let's jump into the virtual Nugget Lab and just look at a couple of strategies when it comes to clustered, non-clustered, and column store indexes. Welcome back to the virtual Nugget Lab. Let's jump into SQL Server Management Studio where we have a new project here, 21.index strategies. And let's start with clustered. And really here I just want to show you the effects of identity versus good when it comes to your clustered index key. So in our Nugget demo database, we have a learner table. And when we designed this learner table, we figured that we wanted to design thinking ahead, thinking we would have lots and lots of learners. So we chose a big int as our clustered key for the clustered index, which was also the primary key. Now I also recreated the table with a GUID rather than a big int. And it has the same amount of data, same everything in it. It's just the difference here is our clustered key is on a unique identifier here. And if we look at it, if we do a select star from learner GUID, and we just change databases here, execute it, you can see that we also have a sequential key going on because that is our default. So fragmentation should be low in this case because I haven't rebooted the server, and any new records that come in should maintain their sequence. So what we're going to try to prove here is that integers are much better than GUIDs when it comes to clustered index keys. In fact, if we scroll down here, I've got a DMV that is just going to query both our learner and learner GUID objects to discover how many pages the data is taking up underneath these tables. So if we execute this, we can see that our learner GUID table takes 143 pages, 153 reserved, and our learner table takes 123 and 130. So right away we can see that it's pretty obvious that integer columns are going to be much better than GUID columns. Now if we create an index on each of these tables, the same exact index on the same exact field here, a non-clustered index, these are going to be based on that clustered index key that's going to use it for their pointer. So if we create these and we go look at them, let's just go into indexes here for our learner table. We'll right click, we'll go to properties on the index, and let's just go to fragmentation. We can see our average row size is 28, our pages are 37. Now if we do the same thing here for our GUID table, refresh, look at that non-clustered indexes, properties, head into fragmentation, 36 rather than 28, and 47 rather than 37. So the moral of that story is to keep your clustered index keys as narrow as possible because of all of our other indexes that we create are going to be based on that key. Let's head into non-clustered indexes. So for this demo, I'm just going to show you how to create an index and then improve it a little bit more. We'll also use statistics.io and statistics time to give us a couple of great ways to look at performance, which is really good when you're dealing with small amounts of data or small queries. So the first thing we're going to do here is just delete our index on our learner table. So that way we currently have absolutely nothing on this table but a clustered index. So let's get a baseline going and then we will index our table. The first thing we need to do is switch our databases to NuGet Demo DB. Let's also include the execution plan here so we can see what it's doing. We have set statistics.io on, which will give us logical and physical disk reads, our I/O statistics, and then setting statistics time on will give us our parse, compile, and execution times of this query, which is really good when you want to know how long the query actually took. So let's execute this. And if we look at the execution plan, we can see that it's doing a clustered index scan. It's scanning the entire index, which is bad because we have a predicate here. We have a couple of filters, so we should be able to take advantage of an index. So if we head over to messages, we can see that our parse and compile time took nothing at all. 14 rows will return 123 logical reads, and it took 50 milliseconds. So I think we can do a little bit better than that. And let's start by just creating a clustered index on the first name, which it should get hit because we are using the first name instead of our predicate here. So let's create that index. Let's run it again. And this time, if we look at our execution plan, we are hitting our first name. So rather than doing a clustered index scan, we're doing an index seek, which is good. And if we head over to messages here, we've cut it down to 34 reads and our elapsed time down to 33 milliseconds. So we got a pretty nice performance boost just by adding that non-clustered index. I think we can do even better than that because if we look at this query, we can say, okay, we're returning first name, last name, address, is subscriber returning and also querying on. So what we can do is create a non-clustered index with included columns that will include these other columns, and we're going to create this on first and last name because we would say, people would probably search by both first and last name. So let's create this non-clustered index, and if we re-execute the query here, we should see in our execution plan that it used our new index, and we should get some performance boosts even further here. And if we look at this, it's just doing an index search against our IX name. See that? So it got everything from the index. It didn't have to go to any other table. There's no other branches here that show that it did any more work other than use the index itself. If we head over to messages, we cut our reads down to 3 and our elapsed time down to 12 milliseconds. So that was a great index to put on this table for this query. Think we can do better than that? It's going to be tough, but let's find out. A filtered index would be good on this query because let's say that we have a lot of reports that target subscribers. We could put a filtered index on that field, which will give us quite the performance boost if half of our learners are subscribers and half aren't. We just cut out half of the data. So we're going to create the same exact index we just did. The only difference here is we're adding a where clause to where is subscriber equals 1. So let's create this index. Let's rerun our query here. And if we flip over to our execution plan, we can just confirm that it did use our new index with our filter on it. And if we head over to messages, look at that. Same reads, but our elapsed time was just cut in half. Pretty cool. So this is a great way to design non-clustered indexes by understanding your query, analyzing it, and then creating all your different index types, analyzing the performance when you execute that query to, number one, ensure that it's using the index that you want it to use, but number two, ensuring that you're getting the performance boosts out of it. Also a great strategy to use when tuning or optimizing existing indexes. All right, let's head into the column store demo here. And for this demo, I'm just going to show you how we can use the column store index against the data warehouse. So let's head up here to our AdventureWorks DW 2012 data warehouse where we have fact tables and some dimensions here. We are going to say our product inventory here. This product inventory table has almost 1 million records in it. We have a nice query here that's going to group it all up, give us some nice aggregates. And if we run this to get a baseline with our statistics IO and statistics time here, let's just switch databases to DW 2012. If we execute this, it's going to take a second here, but if we look at it, we have quite a few amount of reads here, 57, 53, elapsed time 338. So a column store index can dramatically speed up a data warehouse query such as this. And it's really easy to create a column store index because there's not a lot of thought around it. We don't have to design it. We don't have to figure out what our keys are going to be because we're just going to toss all the columns in this table into it. So here are all of our columns. If we look at this create column store index statement here, we're just specifying what table it's on, and then we're throwing every single column into the index that's in this table. So let's create this. And just note that creating column store indexes will take about 4 to 5 times longer. So while we only have 700 and some thousand rows in this table, that didn't take long. But if you're indexing a table that has billions of records, just be aware that that may take a while to create that index. But once it is done, we can execute our query, see what our performance gains look like. And if we scroll down here, we're down to 396 logical reads from 5,700. So that's a pretty big gain just by looking at it. And our elapsed time also went down quite a bit. So column store indexes are great in the world of data warehousing. In the CBT Nugget, we looked at how to optimize index strategies. We started off with an overview where we just went over clustered, non-clustered, and column store index strategies, even got some guidelines there. Then we jumped into the virtual Nugget Lab. We got a clustered strategy demo where we just looked at the effects of an identity column versus a GUID column for your clustered index key. We saw a non-clustered strategy where we just executed a query over and over, adding indexes to it and constantly improving that query by tweaking your indexes. And at the end here, we looked at how column store indexes can dramatically improve data warehousing performance. I hope this has been informative for you, and I'd like to thank you for viewing.